Look, let's be honest. Who here hates math? Come on, raise your hand, don't be shy. Let me see a couple people. Great, a lot of you. Well, I'm here today to tell you that I did too back then. I had this teacher named Christopher. Great guy with a nice British accent, but he really got on my nerves. You see, he used to take off a bunch of points off of all my texts because I couldn't quite use the method he taught. I'd either already know how to solve a problem, or I'd streamline whatever he taught me into something that was easier for me to understand. He sat me down at the start of the year, and I guess I see his reasoning now. He was looking to assess whether I understood what he taught me. But 6th grade me found it ridiculous that I couldn't just use the quadratic formula for the quadratic equation. So we fought for the rest of the year, with me refusing to adapt and him punishing me accordingly. This left me with a great disdain for mathematics in my middle school years. And I think this experience evidences a greater problem with how mathematics is taught in lower education. Math is portrayed as this rule-following subject where all you do is supposedly what's right. We're told that this is how you multiply, that's how you complete the square, this is how you get the volume of a cone, and that's how you use a calculator. And that's fine, but this leaves out a completely different side of mathematics that I've come to appreciate over the years. A side that is creative and rebellious. A side that really is brought to life by the stories behind math and the applications of it. And that is what I want to bring to all of you today. For example, did you know that back in the 16th century, there were math duels? Yeah, duels as in those Wild West standoffs, but instead of guns, it's solutions to problems you would weaponize. And instead of dying, you'd simply lose your job at whatever kingdom or court you were working for at the time. There were a lot of math duels back then, but I want to focus on one between Antonio Fior and Nicola Fontana Tartaglia. Fior had just inherited a formula from his late mentor for the depressed cubic, and he was feeling a bit arrogant, let's be honest. So he challenged Tartaglia because he wanted his job. 40 days, 30 problems. Turns out that Tartaglia came up with his own solution for the depressed cubic and solved every single one of the problems, while Fior couldn't even solve a single one. Tartaglia didn't just get to keep his job from this, he won a lot of pride and fame. We even have a portrait of him today. But he chose to keep his formula secret, still, in the form of a poem. However, one man, Girolamo Cardano, had to know. He pestered Tartaglia with so much hate mail and so much fan mail that he could not refuse, under the condition that Cardano not tell a soul. But Cardano soon takes this formula and generalizes it for all cubics, which is something mathematicians had been trying to do for eons. I cannot stress how much of a breakthrough this was, and Cardano knew it. He dismissed whatever Tartaglia had asked him and published it anyway. Among all the disputes that then ensued between these two, Cardano found that some of the solutions that were obtained from his formula had negative square roots in them. Cardano wrote to Tartaglia, who just mocked him for not even being able to use his own equation, but he was just as stumped. You see, for the longest time, mathematicians had thought of the negative square root as math telling them that no solutions existed. However, when Cardano left these negative square roots in these equations, a real solution would still be obtained. At this time, it seemed that mathematics was abstracting itself from its geometrical reasoning that had governed it up until that point. And as such, Descartes mockingly coined these numbers as imaginary. But they've proven so useful that they hardly seem made up and more like weaved into our universe. For example, Schrödinger's equation, which models the movement of particles as waves, has an eye right smack in the middle of it. That probably didn't mean much to you right now, but it completely revolutionized physics. Physicists have gone insane from the inclusion of probability and statistics and imaginary numbers in a field that was meant to represent the real world. Paul Enherfers, for instance, shot his child and then himself because he couldn't wrap his mind around this. He claimed that the mathematical plague that descended upon all even had come down upon physics. But this isn't the only way that imaginary numbers have impacted your life. You probably wouldn't have been able to get here without imaginary numbers. GPA's tracking systems work because of Fourier transforms, which in themselves work through imaginary numbers. MRI scans, fluid dynamics, market dynamics, electromagnetism, I could lull you to sleep with ways these fake numbers impact your daily life. But most of us never get to hear these applications. Most of us never get to hear the story about complex numbers. Instead, what we see by the time we get to high school is something like this. Lessons, worksheets, tests. Now, let me acknowledge the big leap that does happen once we reach high school. We stray away from simple calculations and embrace mathematical thinking. We're deemed worthy and knowledgeable enough now that we are given a problem and we have to rack our brains to think of what methods we've learned that could solve this problem. And for some of us, this was enough. For me, it meant that I fell deeply in love with mathematics, and even more so with each new method I learned and each new equation I solved. But as much as this is freeing for some of us, most of us have closed our ears to the music by then. We never hear about the stories behind math that really bring in a human element to it. We never hear about the applications and implications that show us how relevant and how impactful these things were when they happened. And as such, our preconceived notions of math as this simple calculations and this rigid thing are overshadowing what we now learn to see as creative thinking and problem solving. Sadly, this is also the point where most of us stop on our mathematical journey. We either choose a major or a career in life where no math is required, and sometimes because no math is required. And other times we'll choose a career that only involves simple arithmetic or spreadsheets. But is this all math is to the modern man? Not exactly. Let me give you a notion of what a mathematician would go through in university and later on in life through group theory. Imagine the set of all integers in the number line with addition. This is the definition of a group, a set of two elements where you can combine them with an operation to form a third. Now I could go on and on with the axioms and all the theorem, I could bore you to death, but I'm not really here because I'm interested in groups themselves, but rather the applications of them, or rather the connections that can be made between these. For example, consider all the ways to permute these balls, or arrange these three balls. Think of all the ways you can order them in a list. What if I told you that by taking each of these balls and moving them to each of these vertices of this triangle, the group of all the ways you can arrange these balls is the same, in essence, as the group of all the ways you can flip and rotate this triangle while still maintaining its symmetry? Weird to think about, no? These often ludicrous connections are called isomorphisms. They're ways to equate a group so that their general structures align. But look beyond symbols, look beyond equations, look beyond just simple math. Think about the group I just talked to you about, the group of integers. Think about how it could be isomorphic, like moving up and down the keys of the piano, or moving up and down the levels of an elevator, or a tug-of-war game where you push back and forth. But I think my favorite isomorphism comes from my summer research I did over the summer with Georgia Tech professor Guillermo Goldstein. More specifically, and stay with me for a second, we looked in converting a subgroup of generators from a free group into a set of free generators through a topological model called color-directed graphs with a series of consecutive epimorphisms and isomorphisms. In case you didn't get absolutely anything of that, this is what that translates to. This is a colored directed graph, and I took a photo of it because it reminded me of Snoopy at the time. See the nose? In In all seriousness, all I researched was the connection between the group of all the ways you can take two letters and turn them into words, the free group, and all the ways you can move around this graph, or all the paths, all the fundamental group of the n rows. And all I did was take the generators of these groups, which are the building blocks, are the ways you can express a group with just a couple elements, and I turned them into free generators, which are generators, but you can't combine them to form the zero of a set. I did this because by getting the free generators, you simplify the algebraic structure of the group, which basically means it becomes easier to do things with. You can calculate with it more easily, you can compute with it more easily, and this becomes really relevant when you're doing thousands and thousands in calculations, like in coding theory or in cryptography. And the series of consecutive epimorphisms and then isomorphisms, they're really just this. They're just collapsing and folding. They don't involve any complex operations. They are just looking at a graph and marking off two edges and just folding them or collapsing them. This is where Snoopy comes from. My entire research wasn't really this complex, mind-boggling process. It was simply visually in play. And that's what I want to get to right now. Modern mathematics can seem really daunting because of its esoteric nature. We often don't really understand a lot of the words when we hear it for the first time, and it becomes kind of overwhelming, like I tried to do with you today. But it's very easy to see how work really becomes play. It really becomes just playing with these things. And I think that's what I've come to appreciate from group theory the most, the fact that so much things can be grouped in the umbrella of mathematics and that it really just turns into play. At this point, if you're not completely in love with mathematics, I don't know what I did wrong. I'm just kidding. Of course, that's not why I'm stood here on stage today. But I do hope you have at least a new perspective of mathematics that isn't just formulas or equations. I hope that you got to see a side of mathematics that has creative thinking, that has rebellious spirit, that has all the real things that encompass mathematics. And I hope that at least 2 or 3 of you today, or a couple more, have been inspired to think for just a moment of what math means to you in this new light. Seen differently, mathematics isn't about following the rules, but rather about bending them. It's about subverting expectations. It's about creating, thinking, exploring. But most of all, it's about thinking and about play. Now, I stood here on stage today and talked about mathematics because it's my calling, and I think it's often misunderstood, but there's also a broader lesson that I want all of you to get out of this. We as humans tend to zero in on the first impressions of anything and everything we learn and treat it as the whole. And while these impressions are there for a reason, it's nice every once in a while to shake it up and try new perspectives, open your mind. I don't want you to see the new side of things just in mathematics. I want you to think about all the things you think you hate, all the activities, the food, the places, even maybe the people. Think about all the restrictive notions you put on these experiences and how this makes you think of them. And consider by how just acknowledging your biases and trying actively to work against them and open your mind, you can start embracing and loving the things you thought you once used to hate, like I did with mathematics. Thank you all.